So up until if you take a look at arithmetic series, um, I guess you could see how it's applicable to you because you are continuing to add a certain number and that number continues to grow. So there's two dynamic parts to it, right? We're making the pot bigger. It's snowballing. It's getting bigger and bigger. And the amount that you add is also getting bigger and bigger and bigger. And so there's two directions. Just as we were adding in arithmetic series, in geometric, we are still adding things together, but the numbers that you're adding, the sequence of numbers that you're adding is actually growing through a multiplication. So if I were to draw a quick picture, you don't have to copy this right now. I just want to give you an idea of where we're going. Before it was like some number, and then the next number is larger, and then the next number is larger, and then the next number is larger, right? And in geometric sequence, we had a number, and the number is multiplied. So depending on what the ratio is, it could be even bigger than this. And then it's multiplied twice, and then it's multiplied 3 times, and then it's multiplied 4 times, so on and so forth. In a series, we take all of these commas and we are essentially replacing them with additions. Whatever that first term was, we're adding it with the second term. And then if there's a third term, we're adding it to the previous. If there's a fourth term, we're adding it to the previous. So you can see how quickly this can grow. In a geometric series, we're doing the same thing, except instead of adding additions, we are adding products that have already been multiplied. So again, depending on what that R is, I think you can see how much more quickly this can grow. This can blow up very fast, right? Remember, this is exponential functions. It's like this. Each one of them has a potential to do that, and we're adding each of them as we go. So it's going to get huge. Now try to use your brain and apply that to money. That's where we're going. So let's take a look at where the equation comes from. I'm going to give you another example, just like the previous lesson. We're going to take a look at how we can derive the formula. You don't have to memorize how the formula is derived, but I'd like you to, again, appreciate the strategy involved in getting this formula and why all the bankers who are using this formula aren't pulling it out of their butts, that there's a reason behind it with math. And then we can use it for complex questions. That's my goal. Here we go. In his curiosity, Mr. Kim is looking up his ancestry, and to his surprise, his ancestors all had only 2 children in each generation, which is a lie, for 13 generations. How many people are in Mr. Kim's ancestry tree in 13 generations? So let's pretend, for whatever reason, we start with 1 person. I don't know why. It's not like they're some hermaphrodite or, like they asexually reproduce. That doesn't make sense. But starting with 1, this person happened to have 2 offspring. And then this person had 2 offspring. Oh, and then this person had, or each of these offspring had 2 offsprings, and so on and so forth. And if I want to know how many people are in the entire family tree, I think you can understand that we're adding here. We have 1 person, 2 people, 4 people, and then next there will be 8 people in that generation. So when n equals 1, that's that. When n equals 2, that's that. When n equals 3, that's that. And n equals 4, that's that. I think you can see how there's a multiplication. But I'm actually not interested in how many people there are in 1 generation. I want to know how many people in total after every generation. So a geometric sequence lesson tells us that the first number is 1. How many generations are there? We're going down 13 generations, so there's 13 numbers that we're dealing with. We're multiplying by 2 every single time. So I know that my ratio is a 2. But again, I am not looking for a term number. No, that's not what I'm looking for. I'm looking for the sum if each of those numbers are multiplied, and that is 1 plus 2 plus 4 plus 8 plus so on and so forth. That's where we're going. Well, how do we know? Well, if you remember, the very last term should still be Tn, which is a times r to the power of n minus 1. I, of course, did it ahead of time, and we can figure out that that is going to be over 4,000. Let me explain. Knowing that this is going to be Tn equals Arn minus 1, if I have 13 generations, that is going to be 1 times 2 to the power of 12, which happens to be 4,096. So how do we calculate the sum? It's great that we know the number. How do we calculate the sum of all 13? When it's multiplying, not adding. So we can't use a previous formula. The formula looks like this, and it's on the back, but I'm going to give you a spoiler. It looks like this. You don't have to write this down because it's on the back already. But I'd like you to consider how this does not have an n minus 1 in the exponent. It's actually a r to the power of n, and whatever that number is, I subtract by 1. So it's the weirdest formula out of all of them. There's no commonality between this one and the ones we've done before. Up until now, we always had a n minus 1, quote unquote. And this is where the formula comes in. Again, now is the time to either pay attention, because you don't have to know this. I just want you to know. I just want you to be aware of the strategy. I try to explain what it is I'm doing here, but I think it's best that I show you. So as an example, if you want to follow along with me, that's great. If you have a highlighter, that's also great. The general sum of any geometric series is the first number plus the next number plus the next number all the way to what? Well, the last number has to be a times Rn minus 1, which means the previous number is a times Rn minus 2, right? It starts from 0 all the way to the number before the n value. And if you know this, like, wow, you actually know this stuff. I appreciate it, but I always have to take a look at how this is done, because I guess I could care less about, the theory behind it. I'm just not wired that way. I'm not as interested in where it comes from as I know how to use it. So it wasn't always like that. I was a really annoying kid because I always asked my sister the why instead of the how. My teachers hated me. And my sister found it annoying, but bless her soul, she didn't give up on me. So here I am. Okay. I am going to, this is pure number manipulation. For the sake of my equation, sake of my formula, I'm going to actually take that entire row and I'm going to multiply it by r. So what I mean by that is, if I took this sum and I multiplied it by another r on the left side, whatever I do on the left side, I have to do on the right side. So this is a times r. This is ar. This is a times r. So ar times r. So this is ar squared. Do you see how the exponent is increasing by 1? Ar squared is now ar to the power of 3, and so on and so forth. So if I'm increasing the r value by 1, then this is Arn minus 2 becomes minus 1 because I'm increasing it by 1. And the very last term will be Ar. What's 1 larger than n minus 1? Just n. And there's a reason behind it. Just bear with me. So that's pure number manipulation. I'm going to multiply by r. And then I'm going to subtract the entire equation here with a normal Sn, which is A, AR, AR squared, ARn minus 2, ARn minus 1. I promise that's as far as I'm going to get you to, right? That's the most annoying part. So after this, it gets easier. But I like you to understand where this number manipulation comes from. Okay? If I took this and I multiplied by an R, the entire thing is scaled up. It has one more R be multiplied. I'm repeating myself. But if I'm subtracting by the sum, if I knew the number, that's basically like some large number minus a smaller number, I guess, right? But here, how do I resolve the differences on the right side of the equation? Well, to make my life easy, I'm going to look for numbers that are completely identical. AR is something here is subtracted by something here. Do you see an AR on the lower equation? Yeah, right here. So AR is subtracted by AR. I can actually cancel these out. AR squared. Is there an AR squared on the lower equation? Yeah, there's an AR. So these two are going to subtract each other and turn into a 0. So I'm going to match them continually in a diagonal pattern. And if you do that, what's left? So I'm going to color code these to try to make it easier on our eyes. Let's use orange. If I do R times Sn subtracted by Sn, everything on the upper equation is going to be subtracted by everything underneath, right? So I can technically say that this AR is going to be subtracted by this AR, giving me a 0. I can also continue saying that this AR squared is going to be subtracted by that AR squared, so it gives me a 0. I can also say, let's continue on. AR cubed is going to be subtracted by the AR cubed underneath. It's going to turn into 0. Let's use a different color. ARn minus 2 is going to be subtracted by ARn minus 2. And lastly, ARn minus 1 is going to be subtracted by ARn minus 1. What is left? On the left side of the equal sign, I have R Sn minus Sn. On the left side, what do we have? On the top portion, what's left? ARn. And on the bottom, just A. So it might seem complex, but again, just forget the math. Just think about it logically. I hope that makes sense to you. From here, I need you to remember that Sn, I don't know what it is, but it is still a number. It could be 100. It could be 1,000. It could be 4,096. It could be anything. That is being subtracted by the same thing here. So I can technically factor out this same number, leaving me R minus 1. Well, if that's the case, take a look at the A value being multiplied by R to the power of n. This is also an A. I can factor this out, and I get A Rn minus 1. I'm going to isolate the sum, the total sum, giving me A times Rn minus 1 divided by R minus 1. You can't see that, so I'm going to write it up here. Sn equals A Rn minus 1 over R minus 1. All of this, which is clearly way too much work to add together, but with a little bit of number manipulation, we can say that the total sum of a geometric series is whatever the starting number is, because that repeats again and again and again, multiplied by R to the power of n. You subtract 1, not the exponent, just a value of 1, divided by whatever the ratio is subtracted by 1 again. And I just want you to appreciate, again, strategy and puzzling and trying to simplify a formula out of something that seems to have absolutely no order to it other than a pattern. Okay. Now that I've effectively just sort of fried your brains, let's see this equation in action. And some of you who are number savvy might also already be trying to apply this to money, to finances. Anyways, here we go. Notice that we could find yeah. You don't really have to worry about that. I'm just trying to show you that there's another way we can write the formula. But I don't think it's as necessary. You, all situations, you should be able to somehow derive the first number as well as the ratio. Okay. Find S9, the sum of the first 9 terms for a geometric series. But even if I didn't say it was geometric series, just said, what if it was just series? You're going to have to test it. So first things first, it's easy to test whether it's an arithmetic series or not. So maybe there's a difference. 14 minus 7 is a 7. Okay. Is it the same if I use a different number? 28 minus 14? No, it's different. It is not arithmetic. So let's try something else. So that's how you test it. Is it geometric? Do we have a ratio? 14 divided by the previous number is 2. Is it consistent if I choose another number? Yes, it is. So this is geometric. The question already gives you my A value, so this I'm already done. S9 is A Rn minus 1 over R minus 1. That is 7. 2 to the power of 9 minus 1 over 2 minus 1. I know that looks so weird compared to all the other formulas you've done, but again, it makes sense. Let's calculate this out. We should get 3,577. Okay. Can we try the next one? Again, for a formula, all you really need is to somehow identify the first number, the ratio, and how many terms there are. Can we try that? Okay. So again, you can pause the video if you'd like, but I'm just going to get to it. A couple of things you want to do. I'll just finish this off so you can take your break sooner and just relax for what, an hour and a half? My goodness. Determine the sum. Sum. So you know that's going to be a series. Being geometric, you know that it's going to have a particular formula. Okay. So each of these is a term. And so you can pretend that this is actually separated, which helps your eyes identify how we can calculate the ratio. The ratio, choose any number, negative 45, and you have to divide by the previous number, that's negative 3. Just double check if you're not quite sure. If you chose 135, will it give you the same ratio? The answer is yes. Yes, it does. So the ratio is negative 3. A, the common letter for the first term, that's a 15. And I do not know what that is. But if I do, I can just plug it into the equation and I'm done. So how about we find out? And erase all this because we don't need it. Let's do it. I know that this is my final term. but being the final term of a geometric sequence is going to be AR n minus 1. Might be a little annoying, but it's necessary. Tn, which is negative 32,805, is equal to 15 times negative 3 to the power of n minus 1. If we can figure out the exponent, we've got our n value, and just plug in the pieces into our series formula. If I divide both sides by 15, I get me 3280515. That becomes negative 2,187 equals negative 3 n minus 1. Using trial and error, what negative 3 to the power of what gives me this? I'm going to try 3 to the power of 7. Yep. Negative 3 to the power of 7 gives me that value. And so, therefore, 7 must be n minus 1, so n must be 8. That is actually the 8th term. I need a bit more space. I'm going to erase all of this, and let's plug it into our equation. Actually, I want to erase it. I'll just make it smaller. What is going on there? Okay, let's plug it in. That's not the term, because that was a term here. The sum of the first 8 terms is a r minus n, or r to the power of n minus 1 divided by r minus 1. That is 15. Negative 3 to the power of 8 minus 1 over negative 3 minus 1. Again, please make note. Negative 3 to the power of 8 is not 7. It is not n minus 1 for the exponent. Negative 3. 1 times 15 divided by 1. Negative 24,600, according to what I just got. Am I wrong? Someone want to double check? The reason I ask is because my answer key has a different answer. I need you to confirm with me. Is that correct? Yeah. I must have done something wrong here. Yes, question. Yes. So you're wondering why is it smaller than the last number? Exactly. Exactly. So this is making it go up. This goes down even more, but this goes up higher and then down even more. And this goes probably going to be a larger plus and then a bigger minus, so on and so forth. Okay. Any other questions? If not, I'm going to go ahead and fix my answer key so it matches what we've just done here. I'll fix my errors and upload them. Okay, I'll pause the video here because we're basically done.